Okay, here is my presentation. Um, I am Evan Tisdale. This is my final project, deep learning. This is my Lego identification. Um, basic. Let's go right into it. Basically, the idea started. I am a huge fan of Legos. I have hundreds of them, and I find that they're both enjoyable and fascinating. But also, if you really have looked at them, you notice that despite however many there are, they're generally all, if you find one of the same category, they're all very similar. And that started making me think about things. So a little bit into Legos. Lego is one of the most easily recognized toys in the world, I would say. I mean, everyone knows what a Lego brick looks like, or at least have seen them in some form. There are literally in thousands of types and color combinations, which makes a huge amount of different samples you can do with them. The nice thing also is that Lego blocks, they're from Lego, the company, they're expected to maintain a tolerance of 0.002 millimeters. So when they do their casting, they have to be very specific in how they do it. So I thought, oh well, if we're that detailed in our set, we could say we're going to get very consistent data, essentially, or very consistent testing models if we wanted to train something, and that's part of the idea. So the problem is I was trying to spin it, was people have already done Lego identification with bricks. So I thought, well, what's something that we could use? Now, the problem with Legos is you have to get a lot of pictures of them, and that can make it hard, especially when there's a lot of pieces that are pretty rare. So a lot of places, people specifically, show in specific, there is a website called Bricklink. And Bricklink is hosted by people, and essentially they find all these parts, and these are all the various parts you can have, and within each part is a bunch of other categories and colors and all different things. And people will sort Legos and sell them on there, and basically get paid for the sorting process. That is incredibly tedious, though, as it should be, considering it takes an enormous amount of thought to look through thousands of Legos and be able to pull them apart and sort them in each bin. And that also poses, in my project, I only want it looked at individual pieces where they weren't amongst many. But let's say you could break down a conveyor belt that fed Legos in an assembly line. You could look at a single piece, like here. Theoretically, if you could scan that, you could have an automated system that could sort it for you. Thus, it would remove the enormous headache it is to sort Legos. And if you were good enough and had all set up, you could theoretically buy tons of Legos and dump them into a hopper and sort them. And that could save you a whole lot of time, and could possibly make you a pretty good amount of money. And so this is where I started thinking, well, how do you sort Lego pieces if you don't have a good data set? Say if you wanted to get started on designing Legos, or sorting Legos, how would you? There's so many different types that you might come across them you're not even aware of, especially if you buy bins from other people. So there is 3D software that actually has Lego models already made, and people have made them in CAD. And if you have every possible Lego already in a CAD software, you could theoretically make your own data set pretty easily too. All you gotta do is take pictures of the block, and now you can add that in your data set. And that's basically where my project comes in, is that what can we do with the realistic renders that they can be used to identify real parts. And other applications could be in factories or on animals that you might not be able to get a lot of pictures of, or really anything. You know, if you can't get a whole lot of data of a big data set for image processing, image identification on what you're looking at, then I would say that this could stand to be one of your opportunities to use 3D software. If you can make a realistic object, or if you need it in a bunch of different backgrounds, you could put it in anything, and you basically can broaden your data set infinitely. I was basically inspired by this guy, Jacques. He has basically a couple years ago he made a screen stitcher parts classifier, and he went through the whole process, and he ended up landing on machine learning. He actually started doing basic image identification, and here's an example of his sorter, and I would highly recommend going and reading. Very interesting. He wrote an IEEE paper as well. In his model, he used the exception model, which is actually in Keras, but I didn't use that one. I would highly recommend that. That's my inspiration for this project, though he was actually he was training with Real, and he basically, as things went down the hopper and he got a picture, he'd basically update it accordingly, and basically was it correct or not, and use that to train it. And then as for the data set that I'm using, I was able to find a data set of Legos. Basically, I was able to find 10 types of Legos, each with 6,000 JPEG image in a simulated form, and then there was also another 600 of these Legos in the actual pictures of them. So if we look at my training set specifically, we can see I have a bunch of different simulated parts. I have a validation set. I'm sure going into more of how I split that up, but it's basically from that set. I basically did a 1% split, or 10% split in my validation, and those are simulated as well. And then my test is the actual pictures of the blocks, and you can actually see the repository I got from GitHub. The person had the pictures with in all different backgrounds, but they were the real parts that mesh up with simulated, so it's really useful and very process intensive, and I'll go more into that later. My environment setup was I used Anaconda, I used TensorFlow with GPU support. I have a 1070 Ti. I use that to basically do majority of this image processing. I would have been in bad shape without it. It really helps speed up the process. And then I use Keras on top of TensorFlow, or use Keras as the front end and TensorFlow as the back end. You can use Keras with Theon or Theonin, I believe. But I chose to go with TensorFlow, and then of course I used Spider, which comes with Anaconda, just to make a Python, and then I integrate over to Jupyter Notebook, which I'll move into on the second half of my project, which actually I can bring up now. So I'm just going to run through my project. Massive amount of imports. I'll let that go for a second. This basically just verifies, this is done on the GPU. I had to set up with CUDA, and it was when I first started, I was doing this on Linux, but I was struggling to get it to work on their Windows. It's just a lot more user friendly, and I was able to get that ironed out to work with Keras and TensorFlow. Basically, right in this step, I define where my data set is, and I've just manually split these up. Nothing too fancy. There are abilities to do automatic splits with Keras, but as easy as Keras is, I was struggling to. It still was a learning curve, and I figured to do the most rudimentary method, which is to create my own 3 models, just to more exercise the concept of this. There's a lot of things that could have been definitely ironed out, but this is a very basic example. Still works though. So let me run that. And you can see there's the 58,800 images belong to 10 classes. So there's 60,000 images total in this data set I got between the in the synthetic, and 6,000 were in the actual training. and these are all split up with using the Keras image generator. They basically generate my data set. If we run here, that's just the define to plot my image. It's just pulled from online. And you can see here, this is synthetic images taken. And a problem I noticed when I started doing this was that the original JPEG images, they're clear when you actually transport them, but when they get interpreted here, they get put with a black background, which I wonder if that caused by, like, given more time, more pre-processing to remove this background or make it consistent. The problem with this data set is that there's a lot of white and black bricks, and there's black and white backgrounds, and I know that skews it, and we'll see that later in the data set with the reel. You'll notice things with the background that matches typically matched better. But anyways, there's a Lego head block, tires, these chairs, there's plates. There's two categories of plates. Let me see if I can find. There's a 2x6 and a 2x8. That's a 2x4. That's another, or 2x8, 2x8. There's a stud, this blue like stud. There's a 1x2 block. There's a 4x1 block. Sorry, I'm just trying to get every type so we can get a good idea. Oh, there's a rod, a Lego rod. There's the 2x6 block, and I think that's pretty much it. There's 10 types, and yeah, I think that's all of them in the 2x1. So those are getting randomly sampled or pulled out of the batches. So then I used the basically come back to our PowerPoint is the model. Well, Keras is really nice, has pre-trained models, and actually the let me see if I can. I went with the VG16. It was very easy to implement, not a very complicated one. They actually did have the exception model. There's also the VG19, and there's the exception model. This was used by the actual guy, and here's some of the statistics for it. I figured it was just one I chose. There was really no reasoning. I just wanted to give one a try, and when I tried that one, it worked pretty quickly. If given more time, I would have wanted to actually compare to Jacques's. He said that exception was working well for him. Given more time, I definitely would have wanted to do comparisons between these to see which actually works better. But for what it was, the VG worked pretty well. So, need to bring that back. Okay, so now I'm gonna down the model, and this is actually this is a nice summary that shows what the full training is, or the full ComNet in every layer. You can see the last part had to be adjusted. The output before was like 1,000 for all the different categories you could have. Obviously, I only had 10, so I had to. You can actually pop out one of the layers, which is what I did right here, and I was able to modify it and add my own, which is really nice. You can actually modify these pre-trained ComNets, which is kind of cool if you wanted to experiment. It shows all the different parameters, trainable parameters. So let me start this running. Basically, I just set. We come back up. I did a batch size of 10 for the training and validation. The target size is chosen for a reason. That's what works. That's what works with this model apparently the best. This model uses a 3x3 convolution layer essentially to do most of the calculations, and then the size is determined by that. Also, if you'll notice, all my classes are labeled. This is so we can actually identify what they are later. Come back down, let this run, and then I broke up the steps per epoch to 100, validation steps 20, epochs 10. Just run it 10 times. Use the atom learning with the categorical cross entropy, and there's actually a binary type that works pretty well as well. When I was starting to mess with this, I started simple and just did one or the other. But if you want to do more than one category, as I'm doing here, you'll want to use this loss. Um, and as you can see, already it did pretty well for accuracy given the 10 and not much adjusting it, but it quickly ramps up in accuracy. Almost doubles by the second epoch, but it does stagger out, and there definitely needs to be some adjustment of the of my parameters that would really highlight, make this better as it keeps going. And then so essentially here, this is where my rendered images, these are being what's fed into the train batches. Those are what's these images are being fed into the model, and they're being used to teach my model what to look for, so I can predict. And it was kind of fun to experiment with it, to see how it worked out. And we'll run it through here. As soon as this finishes, we'll see how accurate it really is. Though the accuracy wasn't this great, I've gotten it up to 70% on some runs. I might come back to that, but let's just go for it and see how it goes. All right, so it's kind of hard to see, so I'll zoom in. So this is where I come into the guessing when it comes to, well, you can barely, it's hard to see. The one thing I didn't like was the messy background he used on some of these. It makes it almost impossible to see. And the thing that gets me is these white backgrounds. I think they really kill the guessing on these images. Like, this isn't the pull, but when you look at the like this, the stud was actually guessed correctly here, and it can vary so much between what background it grabs in the test. So let me run that again, because that looks a horrible amount of predicting. Let me see. Yeah, each one. And essentially, so see, the wheel actually was pretty consistently guessed, and especially a lot of my earlier training things, so I'm not getting good results right now. I wonder if I up the rows, see closer. There we go. That's better. Yeah, and like, I don't. It's very, and I wonder if these backgrounds are what really kills it, especially on the training. If the black is just so overwhelming, it's just not gathering it. But it's from what the synthetic, I guess was the biggest post problem, is that I think it doesn't work very well unless you really train with all these different backgrounds, which I think is something that's kind of the conclusion I got out of this, is that, even with the 70% accuracy, we really should be seeing more of this, but we're using this with a validation set of the render too. So it prompts me, if I could go back, I would definitely take more pictures with other things. But the bigger thing is that the synthetic, without all these background, these possibilities, it kind of throws for a loop of what you could see here. So like, my conclusion has to be, for at least with the current way the current model is, you can't, it's not accurate enough to say with a synthetic, because really we should be seeing better results than this. So yeah, and in that, it is interesting, though. You get a case where like the handle match, and then it draws me to things like the stud. Is it look, because it gets the stud here even in all this, and I wonder and when it gets studs like this, I wonder if it's the angle. Then the handle, it's kind of interesting because is it looking at these features here, and it definitely, which brings me to, if we were going to analyze this, we would probably want to do a bunch of different backgrounds made up to try and help filter it, because when we look at this training set that I trained with and the synthetics, they don't really have, it's just blank, right? I mean, all these are blank, and it's not, I don't think it's getting a good representation. So was a fun experiment, though. I enjoyed it. Definitely, if we could tune it, if I have more time to tune this, I bet we could get closer to this model. Or really the exception model might be the one that Jack Hughes used, and his actual models would be better. But that's pretty much the entire project. That's all I gotta say. Not great results, honestly, with the realistic from rendered. It can get it sometimes, but then it prompts, is it really getting it? But when you look at the accuracy, could more train time help? But and then see, there's cases where it guessed a stud here and it really should have guessed it there. So I'm just not sure. But all right. Anyways, thank you for the class and the lecture. Have a good summer, and thanks for your time.